We're going to start studying electricity. The first concept we need to become familiar with are concepts involving electrical forces and electrical fields. And to understand these, we need to be familiar with the concept of something called charge. We already know what charge is. We are already pretty familiar with this. There's basically three kinds of charge that you can have. You can have positive charges, to be things like protons. You can have negative charges. These are going to be things like electrons. And then we can have things that are neutral. And the primary two types of charge we'll discuss are going to be positives and negatives. And we can use these charges and the relative signs of these charges to figure out directions. Directions the charges are going to move when they're feeling an electrical force or an electrical field. The direction of charges depends on what the charges are relative to each other. So we know that like charges are going to repel. So if I have two positives or two negatives, so positive and a positive, or a negative and a negative charge, those will both repel each other. I also know that if I have opposite charges, then they will attract towards each other. So positive charges likes to go towards other negative charges. And in general, charges are all multiples of the fundamental charge. And the fundamental charge has a very specific definition. It's the charge of an electron. When we're discussing the fundamental charge, we take the absolute value of the charge of an electron. And we know that electron is negative, so its charge is negative value. And we take the absolute value of this, we get the fundamental charge of 1.60 times 10 to the negative 19 coulombs. And that is the fundamental charge, where C, the units of charge, the fundamental units of charge, is going to be equal to coulombs. Now, notation note is that anytime I put something in brackets like this, so you see these kind of brackets, that means that I'm going to be talking about the units of that value. So the units of charge in the SI system, System International, is going to be the coulomb. So now that we know the fundamentals about charges, we need to know how kind of charges act in different kinds of objects. So we have this concept of conductors versus insulators. Now inside of a conductor, your charges are going to flow very easily. Charges move, charges flow easily. These are things like metals. And then we have things like insulators. Insulators resist charge flow. So charges won't flow through insulators. Okay. And then along these lines, we have another thing with how we put charges onto objects. We can put charges onto object by two processes. We'll call one of them conduction, and one of them induction. Now, these would be two ways that you actually move charges around, and typically these are both going to apply to conductors, because conductors actually allow charge to flow. This won't really work very well for insulators, since insulators resist charge flow. So the way that we charge objects is by using conduction or induction. Now, with conduction, let's say I have two spheres, two big balls of charge. And I have some positive charges on this one, and I have some negative charges on this other sphere. If I'm going to charge them by conduction, I'm going to take these two balls, take these two spheres, I'm going to actually touch them to each other. And what I see happens is I have positive charges on the left, and they're going to be attracted to the negative charges on the right. And then correspondingly, I also have negative charges on the right. They're going to be attracted to the positive charges on the left. So my charges are actually going to move a little bit. maybe one of my positive charges gets attracted over to the other sphere and the negative charge gets attracted vice versa. So then I separate these two spheres again. And now I've actually moved some charge. I have two positives on the left and one negative that has been attracted over to the left. And then I have two negatives on the right and a positive that has been attracted over to that right sphere. So I've actually touched these spheres together to transfer charge. That's what we call charging by conduction. Now there's another way we can charge. We can charge by induction. Now in induction, you actually don't have anything touching. Nothing touches. And charges are going to rearrange. You should have experienced this and run into this in chemistry classes with something called polar molecules. This is where charges rearrange. Polar molecules, or the concept of something called polarization, which we'll get into a little bit later lectures. Now in induction, I take my two spheres. Maybe I have positive charges on one, and my other sphere I have negative charges. I bring them close to each other, but not quite touching. So I'm going to have my positive charges kind of rearrange, and they're going to move over to try to get close to the negative charges, which will also move over to one side. So then that means that one side of my object, this is positively charged. The other side of my object kind of loses some of its charge, not as charged. And same thing, I end up with the one side of my sphere being negatively charged up. So developing a very big negative charge. And the other side kind of being left with less charge. And by doing this, I've kind of shuffled around where the charges actually are and the charging that I actually have on my object. I've kind of moved charges around. So I've shifted charges using induction. To actually finalize the charging, I can do various grounding processes where I connect wires to these spheres and make charges actually move once I've rearranged them. We don't need to worry too much about that. We need to be concerned that induction, nothing charges, nothing actually touches, and the charges just rearrange, whereas charging by conduction, your objects actually do touch. So now that we know about charges and how to rearrange them and move them around in charge objects, we can move on to talking about forces. So how charges actually interact with each other. We know that forces from physics 1, these are vector quantities, so they have a magnitude and a direction. We can calculate this magnitude using an equation called Coulomb's law, where the force between any two charges is equal to K, which is a constant, times one charge, times the other charge. We want to take the absolute value of the product of those two charges, all divided by how far apart those charges. We'll call it R squared. So if I have a charge 1 and I have a charge 2, we'll say these are both positive charges. I can calculate their magnitude based on taking the number K, which is a constant. K is approximately equal to 8.99 times 10 to the 9th newtons times meters squared per coulomb squared. And I can take the magnitude of these charges, multiply the magnitude of those, the absolute value times K, and divide by how far apart those charges are, and that gives me how big this force is. So I can get the magnitude of this charge using Coulomb's law. Now the direction is going to come from our concepts of charges. The direction of the force is going to be according to opposites attracting and like charges repelling. So if I look at the two charges that I've drawn up here, I have the force of charge 1. This first charge is going to feel due to charge 2. So to actually denote the direction of this force, I kind of need to draw an arrow of where this first charge is going to go as a result of this second charge. Now, since they're both positive, I know that they're going to repel each other. So charge number 1 is going to try to move away from charge number 2. And I'm going to denote that with the letter F. That's the force of charge 2 on charge number 1. So I like to use subscripts to denote this. And correspondingly for the second charge, this second charge, charge 2, is going to feel a force that repels it away from charge number 1, again, because they are both positive charges. So this is going to be the force that charge 1 exerts on charge number 2. This subscript notation thing I use is something I specifically like to do to keep things clear in my head. You don't actually have to use this. Now the magnitude of these charges, charge forces, it's going to be equal and opposite. So the magnitude of the force is equal. Again, because the charge, the force equation tells us that the force is equal to K times the magnitude of both the charges multiplied together, the absolute value of that, divided by r squared. So if I'm doing force of 2 on 1 or force 1 on 2, that magnitude doesn't change. The only thing that changes for these two forces is the direction. I'm going to be going to the charge 1 is going to go to the left. If I'm talking about the force on charge 1, charge 2 is going to go to the right if I'm talking about the force that's exerted on charge number 2. So this is how we can actually figure out the magnitude and direction for our forces. Something to take note of is the magnitude of the force. Since we're taking this absolute value, the magnitude of your force will pretty much always turn out to be positive. You'll always get a positive magnitude. And the direction will be positive or negative depending on this opposites attracting or this like repelling. So I know that the force of 1 on 2 is going to end up being positive because I figured out my direction of my force based on the sign of these charges. Now the force 2 on 1, that force is going to end up being negative because it's kind of acting to the left. It's acting in the negative x direction. And I got that by using the relative direction that charge 1 was going to move based on charge 2 having an equal sign, the same sign. So let's look at another simple example of how this works in reality. So I have two charges. We'll call charge number 1 2q. That's charge number 1. And then charge number 2 is negative 3q. So these charges, all I want to do is write down direction that the force is going to go. We'll call this number 1, and we'll call this number 2. So what direction are these charges going to go as a result of these signs of these charges? So I have charge number 1 is a positive charge. Charge number 2 is a negative charge. So these charges are going to be attracted to each other. So that means that charge number 1 is going to move toward charge number 2. Now it doesn't matter that they're different sizes of charges, that the magnitudes are different. That just determines the magnitude of the force. The direction of the force comes entirely only from the relative signs of these. Since these signs are opposite, these things are going to be attracted to each other. So I'll have the force that charge 2 exerts on charge 1 is going to move to the right, and then charge number 2 is going to move towards charge number 1. So force of charge 1 on charge 2 is going to move to the left. It's going to be eventually be negative. Okay, so we figure out the relative directions entirely come from the concept of opposites attracting and like repelling. This is important in that in physics 1, you could just plug in some numbers, you could plug in positives and negatives, and everything would fall out. In physics 2, in this kind of electricity kind of work, You get the magnitude from Coulomb's law. Again, the force is equal to K times the absolute value of the magnitude of multiplying the two charges together divided by their separation squared. This absolute value means that the magnitude of your force is always going to be positive. And the direction has to come from knowing this concept, actually knowing the physics that is going on and looking at the actual situation. So you want to get used to remembering the concepts of solving physics problems where you draw pictures and use those pictures to figure out the directions using this concept, opposites attracting and like charges repelling. The final concept we want to get familiar with is the concept of an electrical field. And we know that every single charge out there creates a field. Every charge creates an invisible field. From an introductory physics class, you can think of this field as being similar to gravity. So when I drop an object, I know it falls because a gravitational field acts to pull it down towards Earth. Similarly, every charge has a field that surrounds it that affects other charges that are near it. Okay, so I can figure out what this is. I can have a point charge. Let's say I have a charge of big Q. There's my big charge. And that charge I'm going to say is positive. Now, this charge creates electricity. That electricity is some capacity to do some electrical work, and that capacity it radiates outward from it, kind of in straight lines. So I'm creating an electrical field that comes out from this kind of charged object. If you've ever felt something that's really highly charged, you kind of can feel your hair standing up when you're near something that's very charged, especially in the winter. You are feeling these field lines. So these field lines are just representations of where the field that this creates goes, where the electrical kind of feeling emanating outwards from this charge goes. So it's basically where a charge would go if I took a charge and I stuck it inside of this field. So I have a point charge. This just little dot that I'm going to call big Q. And this point charge, if I take another charge and stick it near this point charge. So let's say I take a positive charge Q, little q, and I stick it inside of this field. Now the electrical field tells me where this charge is going to go as a result of being near this big point charge. So I have this big point charge. I take something called a test charge, a little charge Q, and I put it inside of this field. And this charge, this test charge, is going to go away along this little line. Now, if I take this test charge, positive Q, and I put it up here, it's going to move a little differently. It's going to move away from this point charge, away from this big Q, but it's going to move along this little field line. So every single charge creates an electrical field that looks like this. It's a little bit different for a negative charge, so I can take a negative Q, and we have a convention where the electrical field always tells you the direction that a positive test charge would go. So if I take a positive charge here, a positive little q, and I stick it really close to this negative charge, this negative big Q, it's actually going to move towards it. So it's going to move down. If I take this charge, positive Q, this little, we'll call it a test charge, and I put it right here, it's going to move towards the negative Q. So I could draw the electric field, the invisible forced field, that's going to act on a positive charge due to this negative charge. So I want to just basically to draw the field that I get from any charge. I imagine, where would a positive charge go, a positive little tiny test charge go, if I put it at any position surrounding this. So if I put a positive test charge here, that positive test charge would be attracted and go towards this negative charge Q. So that's the concept behind the field. We can also use equations to actually denote this as well. So the equation for my point charge that my point charge creates for the field is E is going to be equal to F, the force between two charges, divided by something called little q. So this again was, I create a point charge, big Q, that creates my field, and then this electrical field that I get from this is equal to the force from Coulomb's law divided by a test charge that I put inside of this field. So that's going to be the little charge positive Q that I put right here. That's inside of the electrical field that this big charge creates, and that is going to be moving away because the positive charges repel. And I can calculate what this is by this equation. E is equal to F over Q, where this F is the force between these two charges. F is K times big Q times little q over R squared. And I can plug that in right here. So my electrical field is equal to K times big Q times little q, all divided by R squared. All divided by Q. That's my force divided by my charge, my test charge. So I can see that when I do this, my test charge cancels out, and my electrical field is all created by the charge itself, by the big charge that's creating my field. E equals K times big Q over R squared. So these are two different equations that we can use to get the electrical field that's acting somewhere. The electrical field can depend on the force and a test charge that I put inside of that field, or it can depend on just the charge itself that's creating that field. Which equation you use depends on kind of what variables you're given when you're trying to solve a problem. So what I also need to keep in mind when I'm solving problems is the concept that this electrical field is a vector. So it has magnitude and direction. So from physics 1, when we had vectors, we kind of had to keep the x direction, keep different directions separate. So the same thing's going to apply here. I have to add directions for fields appropriately. And if I have multiple charges, and that's what we'll often have multiple charge systems. Multiple charges are going to have multiple fields. And each field is going to go in a different direction. The direction of the field at any point is always going to obey this rule, or these two rules. The direction of the field is always away from positive charges and always going to be towards a negative charge. Okay, so we saw this when we drew the electrical field. Let's see this one more time. Let's draw some field lines. Let's see how to draw electrical fields. The rules to keep in mind for drawing fields. We always start on positive and we always end on negative. When we draw a field, fields don't cross. It's like Ghostbusters. You don't cross streams. The field lines do not cross. And finally, the number of lines you draw is proportional to the strength of the field. Strength or magnitude, if we're going to use technical terms of your field. So I could draw maybe positive Q, and I can draw 4 lines, and all those lines are going to go away because it's a positive charge. if I would then have a charge that's negative 2q, since that charge is double the size, 2 times bigger, instead of 4 lines, I need 8 lines. So I'm going to draw 8 lines. And since it's negative, my lines need to end on the negative. So they're going to be going towards that little negative. So something you might see in chemistry class with dipole molecules. And we'll see this with dipole charges. Say dipole means 2 poles. So I have a positive side and a negative side. And if I draw the field of this dipole, my field goes away from the positive and towards the negative. So it starts, field line starts on the positive, and it goes and wraps around to the negative. So I can draw dipole fields. If I have multiple charges, I can draw the fields like this. It goes away from the positive and into the negative. And those are most of the concepts that you need to get started for understanding electrical force and electrical field.